Check. Good, cool. All right, folks, if I could get everybody to take their seats or find a cocktail round in the back to mingle next to, that'd be great. We're gonna get started here this morning, or I guess afternoon now. So thanks so much for being here for our Masters of Computer Science Projects Day event. Today, we're going to be celebrating students from both the software engineering discipline and the data science discipline. My name is Matthew Hamilton, and I work in the Project Center, and really look forward to sharing the capstone experience that these students have worked on over either the last quarter or 2 quarters with you all today. So a couple of housekeeping items. For those of you here in person with us, you can use the restroom at any point. If you head out to your left, that will be the gender neutral and the ladies' room. Out to the right is the men's room. Please help us eat the food here today. All that we ask is that you don't get up in the middle of a presentation and go get food. So kind of last chance to go get food or coffee or tea before presentation start would be like right now. And then if you do need to take off early at any point today, we just again ask that you don't leave during the middle of presentation. Just leave quietly in between presentations. So presentations are about 15 minutes each, and then afterwards we will have a 5-minute question and answer session. And we do encourage you to ask very difficult questions for these students. They've been working hard over the last quarter or 2 quarters, so hit them with your best shot there. If you are on the Zoom room, thank you so much for joining us virtually today. We're so glad that you can make it. And if there's any technical issues on your end, or if you have a question to submit for the question and answer, please do that via the chat. So with that, I'm going to take a quick step to the side and introduce the Dean of our college, Dean Mitch Shukla here, and he's going to give us some opening remarks. Thanks so much.
Thank you, welcome everyone. This is exciting for us as the College of Science and Engineering. Welcome to the MSCS Projects Day. I know many of your students have worked particularly hard. I wanted to acknowledge first all the professors who have helped our students, and especially Dr. Bay. You have almost half of the list here, so thank you. And I'm really excited also about our sponsors, because while faculty coach and mentor and train our students, but without projects that you bring, Jeff, your team, and others on your team, we would not be having this meaningful exchange of industry relevant thoughts and ideas. So with that, this is really a celebration for students, and I know a lot of work has gone behind the scenes. So the team of Project Center is to get all the credit for putting this show together. Rachel and Aquin are here, but there are others who were involved. Yes, yes. So I just am here to say this is really the flagship experience for our students. Thanks to each one of you who made this possible. I'm looking forward to hearing more about these projects and looking forward to the next steps. Thank you.
All right, so with that, we're going to have our first of 3 software engineering teams present. So this is with DeSimone Consulting Engineers, and it's worth noting that Jeff brought to us a project scope that was so dynamic, and it was a big undertaking that we split it into 2 capstone projects. So you'll hear it from the first of 2 teams today, talking about a cloud control compute system. So with that, if I can get MSCS 24.2 up to the front, we'll get rolling on presentations here. Thanks so much. You can do it on mic. Thank you, sounds good. Cool.
Yeah. I got it. I can do it. Yeah. Good afternoon, everyone. Thank you so much for being here today. We're Team 2, and we're working on the cloud control compute system. To introduce our team, my name is Mahir. This is Duck, Zhao, Sean, and our faculty advisor, Professor Brian Doughty, right here. And our sponsoring organization is D. Simone Consulting Engineering. We've been working very closely with Prateek, David, Jeff, Michael, Andrew, and of course, Team One over the last 6 months to bring this project to life. And so a little bit more about D. Simone Consulting Engineering. They are a firm that specializes in structural design, construction, and construction consulting. And they have a very wide portfolio. They have 13,000 projects that spans 45 states and 60 countries. And the way that they provide their expertise to their clients is through a process called finite element analysis. And this is essentially running simulations of how real world forces such as, high winds, earthquakes, high and low temperatures interact with structures. And they do this through specialized software that runs models. And here's where the problem statement comes into play. These models that are run are sometimes extremely CPU and resource intensive. And the current workflow for these Simone employees is to run this software and these models on their local hardware, which is just regular consumer laptops. And the issue with this is that the level of hardware that they're using is not that great. So that's why it can take multiple days or even weeks for these intense models to finish running. And DSimone would like to increase the performance and run these models faster, and to do that, they need better hardware. But the issue is that the cost of the hardware required is way too high to just buy it upfront. And so the vision of this project was to create something very simple for anybody to use. And this would involve creating a platform that centralizes the submission of these models or jobs, as we call them, and have a singular place where they can be monitored. This platform should also be able to harness higher hardware specifications so that they can increase the performance and run these models faster. And of course, we want to do all of this while saving money. And so our solution is to use the cloud. By renting cloud provisioned high-end hardware, it's just a fraction of the cost compared to actually buying that hardware upfront. As you can see from these prices over here, renting something like a 48-core CPU with 96 gigs of RAM just costs $2 per hour. Whereas if you tried to buy something like that, it would potentially cost thousands of dollars. And of course, we want to provide a user-friendly platform for the employees to be able to submit these models or jobs to the cloud because, Duck is going to be talking a bit more about the architecture of our project now.
So here is our high-level system design diagram. Let's start with the user interact with the system using the UI. At number one, we make a request to the web server to get the file path at number three, and also get the pricing from the external service. While these two are determined, we make a request to the Cloud Job Service API. That's number four, to start a job or terminate the job depending on the situation. And then we trigger the Active Batch service. That's number six. This Active Batch service is managing a pool of Azure machine, responsible for download or upload the input file and output from the file server. And then when the job is finished executing in the Azure virtual machine, we will update the job status to the database API at number 8. And then finally, the database API will calculate the actual cost, the runtime, and also update the latest status in the job database. This whole process makes sure that all the job activity is reported in the system. And next is going to be our milestone.
Thank you, Doug. So these are our milestones. This was over the course of 2 quarters. We started off in September with our main information gathering, learning about the requirements, and designing some low fidelity wireframes for the sponsor to review. In October, we started to go more in depth with our system design. We started looking into how different systems interact with each other. So we had system requirement specifications, API design, and database structure. In December is when the main bulk of our development began. We started doing some UI and started implementing some Agile and Jira to manage our workflow. And this is the point where we started doing the front-end development as well as some cloud service integration. February, we began to start wrapping stuff up. We finished pretty much all the UI and we started wrapping up that cloud service integration. This is when we did have a small minor scope change, which we were able to work with. And now we started shifting more into testing, making sure everything is working. And in March, this is the final phase where we just started debugging, making sure absolutely everything is working as smoothly as possible and get ready to hand it off to the sponsor with the MVP. Next, I'm going to talk about the main user interface layout. We have three main pages: the dashboard, which shows the logged in users' metrics on the jobs, the monitoring page, which shows all the jobs submitted to the service and updates them live, and the submission page, where you submit a new job to the service. So starting off with the submission page, it's a very simple looking page. You put in the input parameters and you click create job, and a job is submitted to the service. We have an estimation, as you can see in the upper right, where you can see the different kind of metrics on the job, like the memory, CPU, and retail price. And in the File Explorer, we do have the option where you can click and preview the file to make sure the file is correct and you're submitting the correct file to the service. Next is the monitoring page, where all the jobs submitted to the service are displayed to you live. It updates. As you can see in the upper right, we have a system to set your update timer from 10 seconds to a minute, whatever you want. We also have a copy to new function where you can start a new job from an old job. For example, if you do have an old job that failed due to, let's say, an incorrect parameter, you can immediately start a new job without having to redo everything. And we have a lot of searching with sorting and filtering to make sure you find the job that you want to look at and sort it based on something like duration. Finally, there's our dashboard page. We have single sign-on. Once you sign in, you get to see all the different metrics about the user and the jobs they submitted. We have things like total submitted jobs and total costs. We also have different graphs to display the more important key information. We have a job type chart to show the kind of distribution of the different kinds of jobs the user has submitted, as well as a line graph to show how well your jobs are doing by displaying how many jobs have succeeded, failed, and terminated. I'll pass it over to Duck with a live demo.
Yeah, so just to note that this demo is conducted in a deploy system with a fully integrated service from the backend. So I'm gonna be the new user, a new engineer at Digimon log into the system. This is what they see when they open the application. So I'm gonna launch the app. And now is because I don't have an account in the system, I'm gonna sign in with Microsoft. I'm gonna use the Digimon account. What the YubiKey? Actually, like you have to use the YubiKey to log in. It's like the company distributed, but right now, like I've put my YubiKey in backpack. So what I'm gonna do is I'm gonna use my current one, which is the same. So I already log into the system. So if I navigate to the dashboard and see all my job is showing on the dashboard. So here you can see the total submitted job, the total cost of all the job I created, and also the latest jobs over here, distribution of on the job. And now I'm gonna go to submission page and then create a new job. And then I'm gonna open Ignite server, use the cloud file server to get the input file. So here I have one input file, click select. Actually, I'm gonna preview this file and see the content of the file to make sure it's the correct file. And then when I'm satisfied, I'm gonna close it and select this one. And then for the output directory, I can select the output directory. Notice that there's nothing inside this directory. Actually, two files that I'm gonna select, and the job will override it anyway. And here I select the job types. Right now we only support OpenC. And when I select the speed slow, you see that the estimated cost and duration is showing on the screen. When you select the medium speed, it's gonna update the price, the estimated pricing and duration. So I'm gonna go ahead and choose the slowest one and create a new job. And then this request is gonna be sent to the back end, and the job is gonna be updated to pending. And now if we go to dashboard for the job ID 64, you can see it. 64 is on the top, is in pending. While we're waiting, I'm gonna do one more with the termination function. I'm gonna do the copy to new, which is copy on the input form that previously created one. And now I'm gonna create a new job, and next I'm gonna terminate it right away. And then this is job 65, terminated. And now the job is being terminated in the backend, and the status is updated into the terminated. Go back to the dashboard, we can see that number 64 is still pending because the backend is spin up virtual machine to run that job. While we're waiting for this job to update to running or succeeded, we're gonna go to the monitoring page and explore a couple of features. Right now, in the running job or the finished job, we can actually filter it by the job type. When I open C, we have two jobs on the menu. And then we can see which one is running by filter it. There's nothing is running. There's two pending, and then we can search it by the name of the creator. For example, I'm gonna search down here for the finished job. Search for the my name. And here is all the job is being created by me. And if I go to the dashboard again and see if this job is actually, yeah, I guess we need to wait a little bit because the job is take a little bit of time to execute. So yeah, that's all the feature that we have. Let's go back to the presentation. Yeah, next is gonna be automated testing by Jao.
Okay, so while waiting for the job to be success, we talked a little bit about our testing process. So we build a CI/CD pipeline with a fully integrated with our development workflow. It's help with continuous improvement and deployment. And we also using Git for version control to track the changes and automate our process. So the picture on the right side is what exactly the pipeline doing after we made a pull request. The system will automatically view and then run all the test case, and then after it passes, it will deploy the new push to the link that we host. And for our testing strategy, we map the database to interact with the database without making any impacts on the real data. We also map the file storage provider, which is Ignite in our case, to test the operation with the files. And we also map the cloud job server to verify our processing logic. We also do integration testing to make sure all the systems work well together. And we use Unix and XUnit for unit testing. For UI testing, we use Selenium. Next slide. So this is our test result. For total, we have 90% for all the layers that we for the other code base. And we have more than 200 test cases in total. And we reached like almost 80% of rain coverage. And let me wrap up our key conclusion. So we successfully implemented all of the features that we planned on the backlog. And this milestone mark our achievement in finishing the development phase. And our current project is stand out as a robust and user-friendly solution. During the process, we learned that the cloud hosting bill can be really large because of the activities such as hosting the website or calling API or connect with other server. Because during the development, we don't receive a lot of feedback from the user review. By doing demo, it's really helped a lot because during the demo, we received the feedback and idea to improve our website. So it's really helpful. And for this project, it's really special because we work with team one. So we technically working a same project, but we are kind of independent team. So we need to collaborate with each other to make the two systems work together at the end. And thank you for coming with us today. Please give us any question if you. Thank you.
All right, any questions from the team here? Well, I can kick us off here. Okay, here.
What was the most challenging aspect?
That's exactly what I was gonna ask you. So the question was, what was the most challenging aspect of this project for y'all?
Yeah, so I can answer that. I think that since our project was split into two teams, I think it was challenging to keep up the same level of communication throughout the entire 2 quarters because as students we have different schedules and stuff. So it was pretty difficult at first to find a time that worked for everybody. And that didn't really land up happening. So we decided to nominate a few people from each team who would meet and then take that information back to the rest of the team. So
Thank you. Any other questions? Anything online? All right. Quiet stuff. Oh, wait, yes, we have the question here. Here, go ahead and talk in the microphone.
So could you tell me what you used for implementing the SSO and how difficult it was to actually implement SSO?
yeah, so
Yeah, I can answer that. So we started off with a template for Microsoft, which is have the authentication built in. So SSO is just really just config the provider, which is Microsoft identity provider. The challenging thing is that is have to config with the Azure single tenant in order to get it work in the company only. So and the rest is pretty simple because we have to build it from the Microsoft already.
Final call? Yes, go ahead, Rachel.
Can you explain how the test branch coverage was 77% while the overall coverage was 90%? Why is the branch coverage lower than the overall coverage?
Yeah, I can explain that. So the coverage coverage is the statement coverage. So we go over every single line of code, but sometimes it's conditional, like we have, for example, less than or greater than, but we only cover that line of less than only, but greater than we kind of cover that branch. So it's usually a little bit lower than the code coverage. So if we cover everything on the branches, conditional, it's gonna go up in coverage. Yes. Does that answer your question? Thank you.
Well done. All right, with that, we'll wrap up here. So let's hear it one more time for team 2 here. We will now hear from our other DeSimone team, MSCS SE 2401. So if y'all want to grab your laptop and come get set up here. Great time to grab coffee or tea or any food here while we do a quick transition. So please bear with us.
Thank you.
Oh, shit, man. I forgot my YubiKey. It's supposed to like use the YubiKey to log into the system. It's like pretty cool. But put it in here. Completely forgot it.
Does it still submit a job to the back? Because that's part of their demo, I think.
Yeah, I submit the job to the back.
Rachel, how's that look?
Take a little bit of time to spend.
The other team needs to be.
At least we gotta get it back up. That was very quick. Can you please mute the microphone?
Oh,
Go back to the
Yeah, they're good.
first slide.
oh, sorry.
Hi, everyone. We're team one for Simone Consulting Engineers. We work on the back end for the cloud control compute system. So as the previous team has already mentioned, our sponsor is Simone Consulting Engineers. We had the honor of working with Pratik, Jeff, Michael, Andrew, and consultant David. They gave us lots of help and let us use a bunch of their resources, so big thanks to them. So our team from Seattle U is Will, Noha, Jonathan, myself, Wesley, and our advisor is Professor Yang. He helped us a lot as well, and so big thanks to Professor Yang. And just a quick background, just to touch back on what Team 2 has already said. Simone Consult is a consulting firm. They provide structural analysis and designs for buildings. And one main strategy that they use was to run simulations on their designs and buildings for natural disasters. And that leads us to the problem that they have left us with. So the problem for our project was that they were having difficulty in managing simulations efficiently, and this wanted us to find a solution to help them run them better. So they wanted us to streamline the process of running the jobs, including the submission for the jobs, monitoring, as well as retrieval of the output data. And they also wanted to create a user-friendly interface that would allow any engineer to use our system without having any prior knowledge of cloud computing. So our solution was to migrate all these tasks to Azure. So we have created an Azure application that will run these jobs so that the engineers will not need to use their own local hardware. The overall procedure of our system is that an engineer would use Team 2's application to input their parameters, their files, and then they would hit start job, and then it'll communicate to our section of the project where it would boot up an Azure instance and then create a bunch of nodes that will end up running these jobs that are hosted on virtual machines. So for the scope of our project, we had to focus on three main things. So the job processing, data management, and creating a robust system for flexibility. So for the job running, we had to start a way to start jobs as well as stop jobs. So for starting jobs, we take all the information passed from Team 2's application and create everything accordingly. And then stopping the jobs once it's done, just to shut down the instance that we just made. For data management, we had to connect to Simone's database system, Ignite. That was just used to gather those input files as well as output certain files that were created. And there was another thing for data was that some files were too large that we couldn't run them through our job runner. So we had to find a way to split up these files as well. And lastly, for the computational flexibility, we saw in Team 2's that you could select how slow, how fast you wanted these jobs to run. So we wanted a robust system that would allow the user to pick low priority jobs you could run it on a slower machine, be a little cheaper, and more higher priority jobs that you need to get done right away. You spend a little bit more money and just get it done immediately. I'll hand it off to Jonathan to talk a little bit about the technologies that we use.
So, yeah, during the first quarter of our project, we did a lot of research on what kind of a surface is best for our project. And first one is Azure Batch. We choose it because it's able to run a parallel and a high computing task in cloud. And it's basically, you can create these tools, job and task, and user can monitor the progress of the job. Also, that another thing that we use is auto pools. That is one of the great thing about Azure Batch. And what basically it does is it changes, or it dynamically creates a virtual machine, depending on the number of jobs there are. And when the job is finished, it automatically, deallocated. And, yeah. Next, we also use Azure Storage. That is where we keep our run apps and important data like details after task is completed. We also have Azure App Service. This is where it's a service that kind of takes care of a growing web apps and API. And in our case, we use it to put our services online. And we also have Azure API Management. That is where it helps kind of organizations to create and understand APIs on large scale. And so in our project, we use it to share our kind of data from our batch VM to Team2 database. Not yet. The SDK.NET right here, that is a service to help the developers who want to work with the Azure services. So, instead of calling like complicated API calls, SDK.NET provide a solution for that. Yeah. And so for Ignite, that is where the DC1 engineer save their files, models, and so we connect our Azure Batch with the Ignite using Ignite API. For C#, we use C# programming language to build our API, and we use GitHub to store our code files and change log. I know this looks different, but essentially it's the same as the Team2 high-level design. Basically, user sending request to our API, and then we run the job through the user batch, and also we can get the necessary data from Ignite and Azure Storage. And yeah, next now we'll talk about some of the service in the API, and he will do a little demo.
Okay, so the main focus for our team was this Cloud Job Service API, which has two main functionalities or two main endpoints. The first one is a start job, which you can use to submit a job to an Azure Batch account and manage anything needed for that job. And the second one is the stop job, which terminates a job in an Azure Batch account. So if we take a look into this start job endpoint. So when a client initiates a request to the start job, it submits a job in an Azure Batch account that we've built specifically for the application. So not each time you'll call this endpoint, it will not create a new Azure Batch account. This already exists there and set up with the applications and everything. And this job is divided into two main tasks, the download task and the execute task. So the download task downloads the necessary input file from Ignite that we need to run our main application. And upon success of this task, the other task runs, which is the execute task. And this is the one where the application that we intend to run actually runs, which in our case is OpenTease. It's the one that is currently supported. And then after everything is done, the output files of the applications are uploaded to Ignite. And during the run of both these tasks, we also contact the database API to update the job status, whether it's running, successful, or terminated, or failed. And at the end, any log files like std out or std error that were produced during the running will be uploaded to Azure storage account. And this way, engineers can use this to keep monitoring and debugging the jobs if something goes wrong, for example, because these files will be deleted as we're using autopools, so the VM no longer exists. So we need a way to keep it there. So that's for the start job. The second one is the stop job, which essentially just terminates a job with the given ID in Azure Batch, and it updates the job status to terminate it. And as we've seen from Team2's demo, they've done an end-to-end user view of how the application works.
So I'll walk you through what happens behind the scenes when you initiate a start job request. So I think, so yeah. So actually we can see here, this is the batch account that we're using for our dev environment, and these are all the jobs that we used for our testing. And as you can see here, there are 2 jobs that ran today, which is the ones that they ran in their demo. And this is the one that was I think terminated, because as you can see, these are the tasks and they're still in active mode, but it was terminated, so nothing ran. If we go back, let's take a look at the one that actually ran. And this is the auto pull assigned. And if we look at that, you can see that it's deleted because the job already completed, and it deletes right after completion. And I'll go back here, and actually if I refresh, you'll see that it's completed. So yeah, as I said, we have a download task and an execute task. If we look at how the view from the task, you can see that it went through active, running, completed. And essentially how a task works in Azure Batch, it's like you're running a command line or a shell script through the virtual machine. So it's like typing these commands in the terminal of this virtual machine. So as you can see here, this is the command that was ran for this task. It's like longer than that. And if we look also at the second one, you can see that it was using applications, which is what was downloaded to the virtual machine in order to download that. So yeah, that's it for the tasks. We can see here for the storage account that's associated to the batch account. We have a container called outputs, which has these log files. And if you look at that, I think I've already, yeah, it's this one. So if you look at that, you'll see download tasks and upload tasks. And these are the output files that were produced, not the output from the application, the outputs from the virtual machine itself. And if the user needs to debug or anything, they can download it from here. So yeah, that's it for the view for behind the scenes for the start job. So let's go back to the presentation. Yeah, okay. And now Will is going to walk us through the deployment and retrospective.
So talking about the deployment, so what we have delivered so far is the development and production environment. These are 2 environments so that if DCE wants to develop their own applications, then they can focus on working with the development and then publishing to production. So with application packages, like Jonathan said, we can use application packages to have our simulation programs version. So if you wanted a different version of OpenSeas, you can do exactly like that. With app services, you can configure the URLs, keys, and also the application versioning, like I said earlier. But this just shows that what we have is something that's easy to develop for production and something that's highly configurable. So next, I'll talk about testing. So what we have for testing are unit tests, and these are important to validate the API specs. We also have integration tests and system testing, and this was all done through manual tests, and they weren't automated just due to the fact that they take a while and they also cost money to run tests. So we thought it would be best if it would just be ran manually. So important part, retrospective. Communication was really key in this project. Every week we had 3 meetings. So we had 1 meeting with our advisor, 1 meeting with team 2, and 1 meeting with our sponsor. And this really helped us to lock down on the project scope and figure out if there were any issues. We can solve that immediately during that time that we had together. There's a lot of research and development. So this project was actually a lot of solving problems with Azure rather than coding. So Microsoft resources really helped us. And I think this is a great lesson to learn. Just it's like learning how to learn, and you have to look through documentation and figure out what problems you need to solve. One last thing is sharing knowledge. This one was really important. Showing other people how to deploy service or how to troubleshoot an issue was really important to us. And I think it will go a long run. So for in conclusion, what we have set up for the future development team is that Azure SignalR should be integrated so they can apply real-time updates. And this was a feature that was originally planned, but fell out of scope. So DCE originally wanted to have something like progress update, display, disk utilization. They also wanted email notifications so that when a job was terminated or succeeded, you would actually get an email notification. But what we hope that we have so far is something has like a solid foundation, something that's easy to extend on, and that's really highly configurable. And all this will be written in the handout documentation to help ease future development. But before concluding, I want to give a shout out to Team 2. Team 2 really helped us with collaboration. Without their help, I don't think this project would have come to life. And shout out to Jeff, Pratik, and David for their flexibility and their feedback for helping this project. And our advisor too for keeping us together. Anyways, thank you.
All right, thanks so much. Any questions for the group here? Yes, please.
Like in the beginning, you mentioned that for large files, you usually like you split those files.
So can you talk about like how you split those files and how you handle those multiple files?
Yes. Yeah. So Ignite API has like an endpoint for like bulk upload, or like I think it was called batch upload or something like that. Chunk upload. So we just split it as like they have a maximum of 200 megabytes for each single file. So that's what we did. We just through the code we like went through the entire files and split it until there were a lot of conditions, and we used their API, which was helpful in that. And we managed, we also solved like if there are a lot of directories, for example, so there were a lot of like recursion in that part. But essentially they already provide that chunk update API, but we had to work with it. Does that answer your question? Yeah.
Other questions?
How does the system detect that the code inside a job is not responding or stuck? Does it monitor the output of the job, the job is generating to ensure it is progressing as expected?
I'm not sure I understood the question.
Could you repeat the question?
Thank you.
How does the system detect that the code inside a job is not responding or is stuck? And does it monitor the output the job is generating to ensure it is progressing as expected?
So when a job fails, it's supposed to send a message to the database. But in the case that the job is running and it fails, it will terminate itself. So that's a feature that we actually need to that we couldn't implement in time. So hopefully that answers your question. Any other questions?
Right here.
So most of the project is actually dependent on Azure. So let's suppose that one decides to use AWS in the future. So is there a possibility of porting this to AWS?
I think in the original scope, they wanted to use Azure, so I don't think there's any plans for moving to AWS.
I'm trying to piggyback on his question about the actual processing. So let's say you made the chunks for the actual file. Does each individual VM get one chunk and run a specific job? Like, for example, if you're doing a high analysis, is one VM running like shearing simulations, one running stress simulations? And did you have to change the algorithm for that, or is that?
Yeah, so good question. So each pool is basically a VM. So like John said, we have auto pools. You dynamically create a pool and it's dedicated for running that specific job. So if you wanted to run a simulation on an earthquake simulation, that pool would be created solely for that job. And then it would deallocate itself to save the costs.
Alrighty, okay, one last question.
Hi, so are there any like security risks when running these jobs? For example, someone can like insert some malicious code into the job and then try to attack the basic one system, for example.
So the DSMO system, if you're referring to the API itself, we trust the information coming from the front end, so that should be enough. And we're using keys for that. So if they could potentially mock the key, then yeah, maybe it would be insecure in that way, but we're using keys to ensure that it's secure. So there should be no way.
Private network.
All right, and that's all the time we have. Let's give a hand to this team. Thank you so much. No, I'd just like to acknowledge, thanks Dr. Dragovic for sponsoring this project. Jeff's a longtime faculty here at Seattle University, and so it's great to have him back as a university partner, and also to acknowledge his colleague Pratik Kaur, who's a recent graduate of the Masters of Data Science program, and recently did a capstone project and is now doing R&D with DSMO. So
by the analysis of all the requirements. The purpose is to deliver a data science product that can be used in real world scenarios. So it includes that a system framework and AI and their solutions to develop this product. And the teams follow the data science methodologies such as the data and acquisition and pre-processing and data analysis modeling and performance analysis. The teams also implement a user interface for proof of concept and write a comprehensive report. The project either took the existing models and we train them with their own data set, or it develops new models and or did a combination work. There are challenges because it's a one core project and 10 weeks, and also it doesn't have a sponsor and that has a very clearly defined requirements. And this is for the modeling part, which is takes a very large computing power, and we didn't have that resources either. And with all of these challenges, and I'm so proud that my students deliver a very interesting product to you today. And please ask them really hard questions, but give them really a lot of maturity and compliments. Thank you.
And with that, we'll turn it over to the rest of the team.
Hello everyone, I am Rajati.
I'm Jay.
And my name is Artaj.
And our project is a retrieval augment framework for meeting and site extraction.
and our advisor is Dr. Ron May, and I'm very much thankful to her. And now, in this fast professional realm, we all attend numerous amount of meetings, and those meetings is a very vital for our platform to share informations and details about the challenges, outcomes, and it's very easy to miss out any details from there, and those details are very much necessary to make any informed decisions. So our project aims to develop a chat interface to help users extract some vital insights from some historical meeting using retrieval generation technique, that is REG models, to enable seamless information retrieval. Now, this is done by grouping meeting based on their abstract summaries and by using a clustering algorithm. This can provide users some precise responses and a high-performance solution for content discovery. Now, I'll give it to Madhu.
Coming to the system framework, we have a user interface where the user would upload the meeting, and this would be taken by the AWS transcribe model where we are diarizing and transcribing the meeting, and we get a transcript that we are giving it to the Facebook BART summarizer that summarizes our meeting. It is an abstractive summary, and those summaries are used by internal clustering model to generate relevant clusters which would have the relevant meetings in that. Coming to the second part of it, that is the question and answer of the chatbot, where whenever a user asks a query, first the clustering model would be executed and would give us the relevant clusters. And each of the clustering ID is tagged with our transcript that is stored in a Pinecone vector database. And whenever a user queries something, we get the relevant context from our vector database according to the clustering model, and that is being sent to our LLM model. And using the prompt engineering, we get a relevant answer for the question that user asks. This is a simple example of abstractive summarization. This left side one is the abstractive summary of our particular transcript, and the ground truth is something that we have generated for the transcript. Our data set contains of 23 meetings. We got it from AMI database, and most of the topics are related to architecture, office relocation, social media, and remote control device. This is an evaluation for some abstractive summarization. We are using word score, where it uses contextual embeddings to kind of understand how similar it is from the ground truth, and it uses sentence ordering, which would give us good results rather than just checking exact engrams if it is present or not. And we also have F-score calculation that is being done using precision and recall. The similarity score is being generated using word embeddings. We take the abstractive summary, we use word embeddings to create the embedding vector, and we calculate cosine similarity with the ground truth embedding and our abstractive summarization. So we can see that we have 86 to 90%. That means the BART embeddings are working well with our particular abstractive summarization model.
Now, for clustering model, this work is inspired by a paper titled More Discriminative Sentence Embedding via Semantic Graph Smoothing, in which they have used 4 polynomial filters: simple graph convolution, simple spectral graph convolution, approximate personalized propagation of neural predictions, and equable graph convolution. Now, for here, they have used k-means as their clustering algorithm. While in our project, we have used mean shift and HTTP scan as a clustering algorithm, and these are the evaluation metrics which are formed by 2 embeddings. First was the sentence transformer, which is shown on the left side, and the right side is when we are using OpenAI
into this evaluation matrix, we are primarily considering adjusted mutual information and adjusted rent index as a evaluation matrix. Now, if we see the upper right one, we can see here that when we are using mean shift with S2GC and APNP as a polynomial filter, the second and the fourth one, the model is performing very poorly. But if we are using DGC as a polynomial filter, that is the third one, the model performs really well in compared with all the models with both the embeddings. So we will be going forward with using DGC as a polynomial filter when we are using OpenAI embeddings to form a clusters based on the abstractive summary which was generated in the prior section.
Okay, so moving on towards the LLM and the RAG evaluation, we primarily have 4 different evaluation metrics. First is the groundness, which measures how well the answer generated by the LLM is supported by the context. Here the context is fetched by the Pinecone vector database for measuring groundness. The second one is answer relevance, where you measure how well the answer is relevant, how well the answer is relevant to the question. Third is the context relevance, where it measures how well the context fetched from DB is relevant to the question. Basically, this identifies how well the Pinecone database is able to fetch the relevant information when given a user grid. Last is the cosine similarity, which helps us measure how basically the answer of LLM and the ground truth. Here, the ground truth for all the questions that we have was generated manually, and obviously, answer was given by LLM. Next. So here is a basic example of all the evaluation metrics. You can see question number 1 and question number 2 are answered correctly. To talk about this sample example, the meeting that we uploaded here was basically a COVID-19 discussion from a hospital where the employees talked about how COVID affects the hospital and the everything else. For the third question, you can see we have asked the question, what is the capital of France? The LLM is able to say like Paris is the capital of France, but this question should not have been answered ideally. But it was answered through LLM's memory. That's why we have answer relevance as 1 and the rest values as 0. Here we compare different LLM models that we tried. So we basically tried 4 popular LLM models. For the first, we measure the groundness. The second is the answer relevance and the cosine similarity. We can see that initially Gemini and Mixed have really low groundness values. This is because these models are so restricted for safety that they are not able to adapt much. This can be fixed or this can be changed using LLM retuning or fine tuning. The second is the answer relevance. We can see all these LLMs were able to correctly answer the questions that they provided. Final is the cosine similarity. For us, the cosine similarity compares answers between LLM's answer and our answer. And our answer was, quite short and up to the point. But LLMs are more verbose. They try to provide an explanation. This happened, that happened. That's why cosine similarities values are a bit lower, but they are able to answer the question right. Now moving to them.
So over here, we will just log into the system and upload a meeting. So it can be a audio file or a video file. We will just mention the name of the meeting, which we are saving over here. It will provide us the transcript and we will be able to edit the speakers, whoever has spoken anything. So I'm providing the speaker names over here and updating it. After that, I will be able to update the transcript itself. So in case there are any kind of additions that needs to be done or any kind of updates, that can be done directly from here. And once we have done the changes, we can upload it. Over here, I am asking questions to the LLM, our chatbot, and accordingly, answers will be provided. After this, I can provide next question. So in this, we are asking regarding the retrieval process. So the LLM will again provide us the answer. And this is the backend wherein it will provide us the specific cluster IDs that we are providing to the system. That is Pinecone. And regarding that, the answers will be provided by the LLM to us over here in the chatbot. So in terms of future work, we are hoping to do fine tuning with QLoRa, wherein we will be able to optimize different LLMs. After that, we are hoping to research further in transcribing models, which can be faster in terms of transcribing the videos and audios into text format. After that, we have embedding models. We have already tested few embedding models, but we are hoping to test even further. After that, we have more LLMs that we can use as in when new LLMs appear. We have video frame tagging. So whenever we are uploading any kind of video, we are hoping to tag the video frame itself, wherein we can go back to the meeting recording itself.
So concluding it really quickly, the project learnings where we learn how to apply the RAG framework and how RAG really works. We also explore different summary, so like different summarization, different clustering types. We have explored different LLMs. We explored how we manage memory in LLMs. We explored different prompts and different parameters that we use. And yeah, that's it. Thank you.
All right, any questions from this team?
So, my biggest question is regarding your context window. Because when you're supplying all this information to your LLM, there's a particular limit on this context window, and how do you manage to deal with that?
Yeah, so talking for LLMs, you might have tried like when you give ChatGPT a lot of information, it fails. It says like the token size has expired. In our case, we are chunking these documents into different chunks and passing it one by one if the document is too big. Whereas for conversation history to maintain, like having multiple question and answers, there's a thing in LangChain known as conversation buffer memory, where what it does is basically it sums up the entire previous context and creates a summary of let's say 650 tokens, and it always maintains a summary for each question. So you ask a question, it generates the previous summary and keeps it in memory for answering the question.
For the clustering, you mentioned that you're summarizing before clustering, but isn't summarizing a lossy process? Don't you use some context when you summarize?
Yes, of course, we use it, but summarization will only help us to divide or cluster all this transcript together and share some basic information so that they can belong like architecture meeting. They have something to discuss about so that we can give LLM not all the architecture meeting, but only that is relevant to.
Fantastic. Any other questions, Rachel? Anything online? All right, let's see what this team. Thanks so much, everyone.
MLCS 20. First, let's take a step back and talk about the opportunity that was presented to our team. So over the years, financial markets have seen an influx of tools, services, and most importantly, data, which offers an array of options in order to make informed financial decisions. However, this range of choices also makes it more complex to track investment watch lists across these different platforms. And so this drives the need for a more efficient solution that simplifies this decision-making process. And this is what StockPicker aims to solve. And so StockPicker aims to solve this by offering a watchlist trading tool where users can manage their watchlist efficiently all under one view. So these watchlists will allow users to track as many stocks as they want on one screen, with each stock containing basic information related to historical prices, such as the current price, near-term and long-term lows and highs, as well as interactive charts for analysis. Furthermore, users will be able to define metrics associated with each stock, such as the alert price, which will help to track the changes according to the stocks over time in regards to this alert price to help these users decide which stock is the best to make an investment with. Overall, StockPicker seeks to provide a user-friendly platform that aids both novice and experienced investors in making these informed financial decisions. And now I'll hand it off to Nicholas to talk about our MVP.
Thank you. So I'd say for the past 3 months of our development period, we're able to accomplish quite a bit of our MVP. So one thing to note that is we have to create a whole financial web app from scratch. So one of our main focuses is to make sure that the functionality works for each of these kind of components that we have. And then at the end, if we do have time, that's when we start to make things look a little prettier. But the functionality is our main priority as we begin into this process. So some of our MVPs include the watchlist page, and then we have a position page where you can track your transactions. And then we integrated trading view, which includes other sort of helpful widgets. And then I think the most important part here is it gives us the advanced charting so that we can actually do technical analysis on a particular stocks. And then we also have a quote page, which is like Yahoo Finance. When you pull up a stock, you can view all the financial data. And then lastly, we use Google Authentication for our login process. As far as our metric goes, we're able to complete about 71 tasks and over 10 sprints over 2 quarters. And within this, the breakdown is that most of these are features, which are 52 of them. We found about 4 bugs and then they are fixed. And then we have about 15 refactors, which are mostly simplifying the code. And then I think next we can kind of go over a quick demo of our web app. Cool. Actually, okay, let's start here. So here's the landing page. So you have a pretty simple landing page for now. Since our main focus again is to get all the functionality in, we just want to create a pretty easy, quick overview over what our web app does. And then we just have a button to log in here. And then if you click here, again, it's a very simple login process using Google Authentication. And if you click on this button and you've signed in before, it will just do an SSL sign in. If you have not, it will do a 2-step verification. But on this page is our dashboard page. Basically, it shows all the market data or market news. And as you can see on the first 2 component here. And then as we scroll down, we have a bit more of market data. again, these are more like market trends, our gainer users and actives. And then if we go back up here. We also have, let's actually go to, let's say you want to search for Apple, we can actually search for Apple here. And then we can click on it. And this is our home page where you will receive different metrics and analysis. And I think the most important requirement here for James is that he wanted a advanced chart. And that's something that we did a lot of research on. And it's something that we can't build. We don't have enough time to build from scratch. So we use TradingView here, and just to give an example, you can actually create a trend line here, and then you can do your technical analysis from here. And then if you scroll down, there's more data relating to the stocks as well as the news. And then other pages that we have are this is the My Position page. So here the user can add different stocks that they have bought. So if I just type in Apple here, click Apple, and if you click add, you'll be able to put in the buy price and then a quantity. And then if you click confirm, it will insert an entry into this grid. And then lastly, we have a watch list. You can actually have multiple watch lists. And in this watch list here, we can add different stocks that you want to watch for. Let's just say I want to type in MasterCard, and you can actually click add, and then it'll ask at what buy price you want to buy it and watch for, and then ask you how many days you want to track the stocks for. And I believe that's it for the live demo. Pass it on to Buddy.
Okay, thanks for the demo. This kind of explains the underlying architecture and how everything has been built. So the tech stack that we chose it for one main reason. We wanted to provide quick iterations so that we could get a lot of feedback from our sponsor. So on the left, we have the user. They access the app through Azure. That's the blue triangle logo there. Everything that the user sees and everything that you saw in the demo right now has been rendered using React. That's what our front end runs on. Login and sign up happens using Google OAuth. This is not a service that we have built. We leverage something that Google already exposes. It's much more secure and much faster for development as well. So once that happens, our main backend server runs on Node.js. So that has two main services that are running. One is obviously charts. That's our charting library. All of this charting information has been populated using TradingView. TradingView is very advanced. It allows a lot of advanced analysis that our sponsor wanted, including drawing trend lines and performing a lot of analysis. That's exposed using the TradingView API at the top right. The second one is a watchlist service. Now that's kind of split into watchlist data and stock price information. So the stock price information that we are retrieving is using an API called Financial Modeling Prep. And all of this data is saved and stored in our backend that runs on MongoDB. That's a NoSQL database. We chose that because we wanted to be able to scale pretty quickly. Duke will talk about testing.
Thank you, Adi. So we applied several testing methods to make sure that our project meets the requirements. And we have the first one is unit testing. So we focus mostly on testing the backend related methods since they are the core of our project, and we wanted to make sure that these features work properly. And yeah, we focused on testing the database models and data handling operations like querying, insertion, updating, or deletion. And yeah, for the tools, we use Chai, Mocha, and Shinan for mocking and creating test suites and assertion as well. We also apply integration testing. So since we wanted our integration testing to be as close to the production environment as possible, we use Supertest to test the process of calling APIs and receiving responses. So we can validate different cases from happy cases to the error cases as well. And we also faked the MongoDB by using a tool called MongoDB memory server. So it stores all of the data inside in memory, and when the test is done, it will release on some. Yeah. And last but not least, we also apply regression testing as well. So every time we update, fix, or add a new feature, our tests are automatically run again by a tool called Husky. And every time we push something onto Git, the test will be run again to confirm that all the tests have passed. If something is broken or maybe the test is failed, then we won't be able to push onto Git. So yeah, that's how we do regression testing. And we also have like a CI/CD pipeline. By using GitHub Action, we were able to have real-time updates for our application. So whenever there is a merge to the main branch, the GitHub Action pipeline will be triggered, and it will use PM2, which is like a process management for Node.js application, and it will automatically review our application and deploy it onto the server. Yeah. And last but not least, I'm going to talk about security. So we also apply several security measures to make sure that our application is secure and safe to use. We have TLS, and we also apply authentication via Google. We also store our secret keys via environment variables locally on the server. And the server can only be connected via SSH. And yeah, we also enable firewall so that only certain ports are public, so that we know that which one can be accessed from the users. Yeah, and I'll pass it to Anupurna.
Right, thank you. So now that our MVP is done, in terms of what's left for our team, it's basically handing over all of our documentation, all of our code, all of our accounts over to James. But apart from that, in terms of the work that if we had more time, we could get to, it's, as Nicholas mentioned, improving the look of the app, making it a little bit more visually appealing. And then secondly, extending the login functionality from just users who have a Gmail or a Google account to all types of users. If you have Microsoft, if you just want to create your own username and password and log in that way. And then finally, in specific to the My Positions page where a user can log their transactions, being able to integrate our app with any brokerage accounts that they could use, like Webull, like Robinhood or Fidelity. And so if we had more time, we would probably get to these, but they will probably be passed on to the future teams that take this forward. In terms of our lessons learned over these past 2 quarters, primarily we focused on 3 aspects. Number 1, communication. We found that communicating with our sponsor and our advisor and within our team, and meeting regularly and having that regular contact really informed the decisions that we made, as well as informed us to be proactive in our decisions and how we executed, when we executed, what we executed. Secondly, balancing our feature complexity with our timelines. This we kind of took from last quarter. Being able to balance all of the things that we hopefully want to achieve within our app, and also balancing that with what is actually realistic to complete within the time frame that we're given. And then thirdly, our documentation, being able to write down our rationale for the decisions that we take. We found it really helpful to refer back to last quarter's documentation in that we were able to see what MVP priority features we wanted to get before you today. And be able to structure our development so that we will be able to execute it fine. So that's a wrap for our presentation. Thank you so much for listening. A big thank you to James for being the sponsor, being able to dedicate so much time and effort in helping us and making this project what it is. Thank you so much to Jason for spending every week giving us guidance and advice. And I thank you to the Project Center for organizing this and bringing a space where all of us can present what we worked on today. And so that's a wrap for our presentation. Here is the URL and QR code if you would like to access our website. And we can take questions.
All right, any questions for our final software engineering team? Coming to you.
There is a module where you're showing the news of, recent news. So where are you getting that data from? Are you storing it in your database, or are you like calling any API, or are you doing any web scraping for that, the top stories?
Actually, so we're not really storing any data for those stories. So this component actually is a like a package that we thought that comes with TradingView. But if we actually have more time, the API service that's providing all the financial data, we're going to call it the FMP or financial monitoring threat. I think we have more time, we actually would have used that API instead and create our own UI component. And then because that I think provides more data than what TradingView currently provides. But yeah, to answer your question, we're not storing any data at all regarding stories.
Excellent. Any other questions? Rachel, anything online?
So I believe like this data, the website data is storing into like database as well. So is it getting stored, the stock price data in the database?
Yeah, I think Duke could expand a little bit more on that. So a lot of these data we don't store. However, he did mention that we are using cron job to help facilitate the number of API calls. Do you want to expand on that?
Yeah, sure. So for some parts, we used the data provided from FMP directly. But for some, since the users may have access and may query those data frequently, that's why we need to minimize the total request to the third-party API. And for those data, we store them in our database by using a cron job. And that cron job will periodically call the third-party API, for example, once a day, so that we can get the up-to-date data, and then we will display it to the application.
Like, so it's not live data that you are showing here currently.
So for this page, all of the data here is up to date, but for the watch list page, these data are stored in the database.
Okay, thank you.
Coming to you, James.
Awesome, and this group did everything from scratch, so yeah, please give them a round of applause. Asked to do in this project because we're doing it from scratch, and they're talking about more things like UI and the way it looks, but I think it looks great the way it is. They did a very good job. Overall, I guess the question for you guys is, what was more challenging? Kind of coming up with the plan to create this, or after the plan was created, doing the back end work and actually making the website and the functionality of it.
I enjoyed a lot of the backend stuff, figuring out what tech stack we're going to use, how that integrates into everything, and thinking about it from a long-term tech perspective. I think that was pretty new to me. I was trusted the role of architect. I had to figure all of that out. It was a lot of fun interacting with all of them on them and figuring out all of that, and then also I think somebody else would probably speak for non-tech side. Yes.
Sorry, I'm going to talk about take a second. Yeah. So for me, I really enjoyed researching and handling the pipeline project and also figuring out how to test our project effectively because I used to like work on some projects that not only like did test manually, and it was painful once there is an update on code and as well the features. And for the pipeline, if you like do it manually, there will be like human errors, and at some point you will like accidentally deploy really like faulty version of your software. So yeah, I really enjoyed that process. Yeah.
For my end, I can speak to kind of the non-technical bit. Yes, the technical bit was a little bit more hands-on, and there was a lot to learn in implementing what we implemented. But I guess for the actual conception of the idea, it was really interesting to go back and see what brokerage accounts. For example, my mom has a Robinhood account. So going and looking at that and saying, okay, this is kind of the way it works. And this is the difficulties that we endured that Robinhood probably endured tens of thousands. And so that was really interesting, but also challenging at the same time to see, okay, this is how the real world stock applications work. But yeah.
Awesome. And that's all the time we have. So let's give this group one more round of applause. This is special thanks to James for supporting this project. Hopefully there's future iterations. I'm blown away by what your idea when you came to me last winter and what it looks like now. So yeah, awesome. And thank you, Professor Wong, for the support here. All right, so next we will move on to Data Science Team 2. And we are kind of shuffling the data science schedule now. So the remainder of the schedule will be Data Science Team 2, then Data Science Team 4, Match Outcomes. Then data Science Team 3, Walk Explore, and then last but certainly not least is Data Science Team 5, Sign Language to Speech.
Check it out, and then make sure you are muted good. Yeah, I'm muted. Everything look good? Right, great, cool.
Good day, esteemed guests and colleagues. I'm Aditya Gulapalli, together with my team, Srimitra, Shrikant, and Vaishnavi. We are thrilled to present our project Legal Sense under the mentorship of Professor Vanve. Our project aims to tackle the emerging challenges posed by AI in legal contexts. Our journey began with the realization that the AI landscape is evolving rapidly, especially in the field of text generation. Open source tools like Google's Bard AI have blurred the lines between search engines and legal assistants. A striking example is the case of attorney Michael Cohen, highlighting the misuse of AI in fabricating legal documents. This underscores the critical need for a system to assess the authenticity of such documents in legal settings. The core of our project is addressing the increasingly complex challenges posed by AI in text generation. And our world is rapidly embracing AI technologies, but their integration into legal contexts brings unique challenges. The risk of AI-generated documents being used inappropriately or inaccurately is a significant concern. To combat this, we've developed an ensemble model. This model doesn't just classify documents as AI-generated or human-written, it also estimates the likelihood of the document being AI-generated. This is crucial for making informed decisions in legal matters where authenticity and accuracy are paramount. Moreover, we've also integrated abstractive summaries and readability index scores in our UI. These summaries and scores distill the essence of complex legal documents, offering quick insights into their key points. For our project, we needed a diverse data set. This was sourced from courtlistener.org. It's an expansive repository of legal documents. We specifically focused on court opinions under Washington state jurisdiction and various other courts to ensure a comprehensive and a relevant data set. This data set includes 800 documents with an equal split between 400 human and 400 AI generated data. For the AI generated part, we used the existing 400 human written data using ChatGPT API, employing various temperatures and prompts to create a range of AI generated text. This diverse pool of data was essential for training our model effectively.
So based on the data insights, the first one represents the text length graph. And we analyze that the left side measures the AI generated text. And in terms of the text length, they follow a narrow distribution, and this represents the uniformity. Whereas in case of human generated text, they follow a broader distribution of text length because it was written by legal professionals and they follow different structures and different comprehensions. Poststat, this represents the part of speech that will categorize the labels, like that will categorize the grammatical labels to the text. And for the AI generated, the noun tops the chart. And this means it is useful for writing an informational or technical paper, but not for the case, like for the court context. It's because we don't address people by the name. We address them by victim or the convict or the defendant. In case of the human generated, they follow a strict punctuation and they follow a formal structure, and different professionals have different writing styles. The readability index score that measures how easy it is for the reader to analyze to understand the text. So this represents the text standards that varies from the middle school to the higher school to the university level. There are different text grades, and we have two peaks. So the first peak represents the human generated, and the peak is from 9th and 10th. And if we go through the higher level, the peak for the human AI generated is 12th and 13th. On analyzing the normal distribution, the mean, we get like 12.2 and 10.2 values for human. We also performed another criteria for analyzing the readability scores, and there are like different criteria. So here we concatenated all the 400 documents for human and all the 400 documents for AI. In terms of AI, we got 13th grade for the text standard and 21st grade for the human text standard. This is a bit contradiction, and we needed like further investigation by adding few more large volume of data sets. Next is the system framework, and we have, for this model, we have separated the task into 3 phases, the phase 1, phase 2, and phase 3. In the phase 1, we extracted the raw text, and to perform the abstractive summarization, we used BART, and we also analyzed the readability scores. For the same, we use the same raw text to tokenize the text and then pre-processing the text. Also, all these texts, all these inputs are getting processed to the ensemble model, which will be explained in the later slides. And we will get like 2 kind of outputs. One, if it is being AI generated or not. And also it will predict the likeliness, like how much percentage it is being AI generated. And all these outputs are getting displayed in the phase 3 as a UI display. So we have the likeliness and the summarizations, and everything will get displayed as soon as we add the input file.
Right, as Vaishnavi explained, we use simple Facebook CNN model part to provide an abstracted summary of the legal document provided to us. And for the actual purposes of the project itself, we use an ensemble model made up of 4 different models and a voting classifier to give weightage to those models. And the output is just a probability of the legal document being AI generated, and it's also classified based on the threshold value. And the first model we use in the ensemble model is the multi-object 9-based classifier. It's a probabilistic algorithm which classifies text document based on the words inside the document itself. So what it basically means is that it takes the words and tries to give it a value to show if that particular word is more probably in AI generated document or a human generated document. And then taking all those scores, it classifies a document as an AI generated one or a human generated. And the second model we use is the stochastic gradient descent classifier. It's an optimization algorithm which it tries to minimize the loss function inside the model itself. What it does is it basically gives random parameters to the model and then loops through a structured data set to find the best parameters for the model itself. We also have 2 different gradient boosting missions, the HBM and CAT boost to further optimize the ensemble model itself. And the data we have is split into 75-25 split, where 75% of it is used to train the model and 25% is used to test the model. And to just check the performance of the model itself, we have a couple of metrics. The first one being the raw box score. It basically gives the area under the curve itself, and the more the area we have under the curve, the better score we have. It shows how fast we can have a high amount of true positive rate as compared to false positive rate. And the graph we have over here is the first graph we had when we actually ran the model itself. This is the baseline model. We had around 78% of area under the curve. And this is the final model we have. We have around 96% of the area under the curve, and which is a pretty good improvement as compared to the initial one. We also have a couple of other metrics like the precision recall and reference score. And this is the initial scores that we received when we ran this segment itself. And as you can see in the recall version of the AI generated one, we had just around 0.962 as compared to 0.304 for human generated. And it showed that there's a very big bias towards AI generated documents initially. And this is the final results we had, which is a very high, it's a really good results compared to the initial baseline one we had.
This is how the UI looks once the app has been launched. On the left side of the UI is a sidebar with options like to upload a document and few other features that I'm walking through. Let's start by uploading a document and see what it does. So once a user uploads a document, our model takes approximately 20 seconds to analyze the document and then produce the classification. Along with that, it also gives the likeliness of the classification. If a user wants to check which document they have uploaded, they can do so by clicking on the view document, which is on the sidebar. It gives a quick look at what the document is. And then apart from the main functionality, which is to predict the classification of document, if a user wants to get insights from the document he has uploaded, he can do so by clicking on the document insights button. So this gives a simple bar plot with different readability metrics, which shows how easy this document is for reading. If you want to get an idea about what these readability metrics are, you can click on the Get Insights Expander. The most appropriate and the accurate metric for judging the readability of a document is the pledge readability keys, which says that this document is pretty standard to understand, and it gave a score ranging between 60 to 69. And all the other metrics that we display are shows that the level of education one must have to understand this document. The small and the flesh KitKat scores are the most appropriate ones for our use case. which says that a 12th grader and a 10th grader should be able to understand this text pretty easily. Let's try uploading another document and see, let's compare the results with them. So our model says that this document has been written by a human with a likeness score, and then the readability scores for this one. And the FRE score suggests that this document is fairly difficult to understand. And the SMOG and Fleshkin-Cat scores also say that 14 and 11 readers should be able to understand this text. By this, we can say that the human-generated documents are more complex to understand for a user than the AI-generated ones. Apart from this, we also have another feature which gives the summary of the document, which is a quick way to get an understanding about what the long document is. And also, if a user wants to compare the summary with the original document that he has uploaded, you can do so by clicking on the expander. That will be the demo. So we have implemented most of the things that we have been planning to do from the past 10 weeks, and we are pretty happy with the result that we have got. But like any data science project, there is always room for improvement, and we also have some options where we can improve in the future. Like the abstractive summary we have implemented in our project, which is quick and an easy way to understand the document, but an extractive summary which grabs sentences based on importance would be a better way to give a summary, which will also help legal professionals better with just a button click away. And then by using any of our methodologies, we wanted to display the facts like name of the judge, location of the case proceedings, etc., which will also be pretty good information to display. And then for the UI, we have used Streamlit, which does its job, but we would like to implement cache preservation, which will help us to cut down the runtime between each functionality. As I said, we have implemented this project mostly from scratch, from the dataset creation to the UI implementation. Most of the things were done from scratch. The hyperparameter tuning and the evaluation metric helped us in getting a better accuracy. Like we have started from 90, we have started from 70, but by tuning it, we got a 95% accuracy. And there are many algorithms that are available to develop an NLP classification model. So we studied our data, went through our options, and we have selected this route. And then we have used different transformers for pre-tokenizing our data. And then these are the learning outcomes that we got throughout the journey of this project. And then all in all, this has been a rewarding yet a demanding journey. We'd like to thank our advisor, Professor Warren Gale, for being our support throughout this journey. Any questions?
Any questions from the audience here? Come here.
Saw that there were a lot of evaluation metrics that you guys displayed on the UI. Like, and all of them have different outputs. Could you like one?
So different metrics use different textual features. So different metrics use different textual features like number of words that are present in the document, the average number of syllables that are there, the number of sentences. Based on that, it gives results.
Any other questions out there?
So just a follow-up question, you answered that there was good, right? Yes, you use different metrics, right? There are more metrics that could have been used, right? So can you explain to me why you took, like, did you try other metrics and why did you choose to use the metrics you chose?
So we have used the most appropriate and the accurate ones, which is the flash readability yields, which gives a score ranging from 0 to 100, but anything more than 60 is a pretty good score for an audience to understand. And apart from that, we have mostly concentrated on the level of education one person has to have to understand the text. So that is why we have chosen smog and the flesh skin cat score for our metrics.
You have created an ensemble model. Since 4 of them, you have given the weightage. How did you come up with the weightage for each of them? We didn't exactly have a specific model, specific method for coming up those numbers as well. But the last 2 models, the GBM and CAT, those are basically gradient boosting algorithms, so they didn't require much weightage itself. And most of the heavy work is done by the SGD and MMT, so we provide the most of the weightage of those 2.
All right, that's all the time we have for this team. Let's give them a round of applause. Thanks so much. Next, we have our match outcomes team, data science team 4, I believe.
It's Mike team now.
I'll plug in for it to open up that sentence.
Gotcha. Thank you.
Yeah, it just takes a second.
So I dare try and bring it up for the screen. I believe so.
Go to share.
Oh, yeah.
Thank you. And the screen desktop too. Great. And then you are unmuted, so that mic is live. Right. You should be good. Maybe just click.
Great, thank you.
You should be good. Oh, good.
Hello, this is Owen Clinton and I'm Ulysses Lin, and our project is called Predicting Match Outcomes using heterogeneous temporal graph attention networks. With the ubiquity of social media, online shopping, and streaming services come complex time interaction data. What this means is you can have various different types of actors as well as events. So predicting events in this space traditionally required extensive domain knowledge or feature engineering. And what we wanted to do instead was to learn from complex relationships among different types of actors over time. And we do so using something called temporal heterogeneous graph attention networks without feature engineering. So a domain where predicting events based on historical interaction data is crucial is in sports or esports, also known as video games. Predicting match outcomes is pretty useful when you want to assemble the best players for a team or in sports betting. And existing methodologies are unable to fully capture the dynamic nature of relationships, or the models are only geared towards one specific sport. Additionally, a problem that we also saw was a lot of models only predict on ongoing matches. We wanted to use historical data that was in a model that was feature agnostic and thus generalizable across different sports. And we do so on 3 different data sets. 1, League of Legends, which is an esport. 2, the NBA. And 3, soccer. So our model utilizes a graph structure. What this means is you have nodes and edges. For nodes, we have players in light blue and teams in dark blue. Edges are the interactions or events that happen among different nodes. For example, you could have a home team here losing against an away team, or also a home team winning or tying with an away team. Additionally, so features get encoded into an m by m array, n being the number of edges and m being the total count of features. Different edges can have different features. Some examples of features might be damage done to an enemy in League of Legends, or number of three-pointer shots in the NBA. Here we have a graph example. To the left is the example in tabular format, and the equivalent of it is in visual form in the right. So at the center at the right, you can see that team 827 has lost to 391. This gets encoded as an edge type of 1 for loss. And we see the equivalent of that in the third row over to the left, 827 and 391. We can also see that player 2977 joined team 391. That gets encoded as a 3, and we can see the equivalent of that in the table, row 2. Every single interaction or edge has a timestamp associated with it. And the features column to the far right on the table, this is a non-literal representation of all the different types of features that we want to encode in. So now Owen will talk about the model.
So the model we use is called TAN. It comes from the paper Memory Enhanced Transformers for Representation Learning on Temporal Heterogeneous Graphs by Lee et al. It uses attention mechanisms to encode node and edge level embeddings from a graph. And it's supplemented by a memory module, which allows for sort of more historical learning by storing historical information on nodes. We chose it because it's a state-of-the-art model with best-in-class results for temporal heterogeneous link prediction. So to sort of go over how the model works, it's split up into many different sections. So first step is that edges marked with prediction classes are passed to the model in sort of chronological order. The edges are then fed into a temporal convolutional layer where we sample n neighbors for L layers of the model. After that, some of that information is stored on that memory module. And then the nodes and edge embeddings that it sampled are all transformed into a shared vector space. These vectors are then passed to the attention mechanism, which outputs embeddings for the original node and source nodes, which are then passed to a multi-layer perceptron, which gives a prediction that an edge exists between that source and destination node. So our contributions to the model encompass sort of converting it to a multi-class predictor. The model originally was provided to predict graph links using negative sampling, where two edges, one that it knows exists and one that it knows doesn't exist, are provided to the model, and it just predicts whether each of those exist. We needed to predict sort of the type of edge or multiple types of edges in our graph. So for example, if we have a situation where in soccer, Manchester loses to Liverpool, instead of just having a loss that exists and an edge that doesn't exist, we instead provide the model with all three possible outcomes for that soccer match. So either wins, loses, or ties. The model then outputs a prediction for each edge type. So we see sort of like each edge type numerically and the probabilities that it exists. And then we sort of choose the only one that exists and score based off of that. Here's sort of a system overview. So we sort of take our data in tabular format. We have to convert that into a graph. It then is sent to the model. Predictions are made on it. We score those predictions, and then everything is backpropagated to learn. And then sort of for our downstream, when we want to query or test the model, we can send sort of new graph data or a specific query that also gets converted into a graph. Sort of we get predictions output, and then we send it or use our own graph visualization that we built. The data that we use, so we have 3 different sports. We have soccer, NBA, and league data. The soccer data set is from the European League. It encompasses about 20,000 matches. The NBA data, we took sort of every game up to a certain point since 2021. That is about 3,600 matches. And for League of Legends, we took the past sort of 10 years of matches in professional esports, which is about 73,000 matches. And for soccer, we were not able to get sort of game level features out of it. So for NBA and League, we do have game features that we can include in the graph. And you can see sort of the difference in graph size, whether or not we include features. So for the results, we have sort of the class ratio. So in the graph itself, what ratio of edge types exist. So you can see in soccer, sort of 45% of matches that are 45% of the matches the home team wins, 30% the home team loses, and 25-ish% is a tie. For NBA, sort of 56% the home team wins, and for League of Legends, 53% the home team wins. And then, so for our experimentation, we did 10 runs of an 80-20 train test split. And for the graphs where we could include features, we ran it twice, once without features and once with features. And then, so we scored it based on accuracy, just how many matches it predicted correctly. The standard deviation shows the difference in accuracy over those 10 runs. And the favoritism percentage is sort of how often do the favorites in this sport win. So, yeah. So what did we find? We found that at this point in time, the general model is not yet performant enough to beat traditional approaches utilizing feature engineering when applied to non-feature engineered data. But we did find that the model is able to learn given only the base graph structure. So you could see that instead of just predicting the most common outcome, it actually is able to outperform that a little bit. And adding features to the graph improves model performance, but in the case of the NBA, it increases the variance in model performance between runs.
We wanted originally to be able to visualize the entire graph itself, but this would become very cluttered as you have many different types of nodes and edges floating around. So instead, we thought it would be more practical to focus. In the case on the left, you can focus on 2 different teams. And this is more useful because you probably are interested in whether one or the other team will win or lose. You can also focus on a particular node. For example, we'll see later in the demo, like a player or a team. So we'll play a demo for you now of the graph showing League of Legends. So to the left, we have the sidebar that allows you to choose the home team as well as the away team from the given list. Or you can simply input the team numbers. When you submit this, you will see a singular edge for every single event. And this is very confusing because a single player could join the same team many times throughout history. It was a little confusing to look at. So instead, you condense the edges so that every type of edge between 2 given teams is shown as 1, and the thickness represents the number of actual events that it represents. So here we see the home team losing to the away team twice. And then Fiesta, the name of the player, he joins the team Nongxin 5 times. This is the number of the team. You can also display just this single time span, or if you want, you can choose one match that was played between the home and away teams that you specified. Now, we only tested on a fraction of the data. If you were purely interested in those edges that were tested by our model, you can also show that with predictions only. This is a very simplified demonstration of that. And we'll hone in on an example right here. So as you can see, the home team won against the away team a bunch of times, I guess 7 times here. And in the first row for the April 30th match, we predicted there was going to be a 55% chance loss, and that prediction was incorrect. But on the May 8th match, we had a 50% chance of win prediction, and that was correct that time. So you can hover over these edges and see exactly what we tested out and see if we were correct or not. In addition to being able to focus on different teams, you can actually do node adjacency. That is to look at, for example, a singular team, A27, see all the players that joined it through time, or the other teams that had played. Alternatively, you could focus on a single player. For example, here we look at player Lancer, who joined Kwangdong Freaks Academy many times. So what did we learn from our project? We learned that we were able to generate, visualize, and experiment with graph data. And we were able to take an existing model and adapt it to the specific needs that we had. We learned that the graph structure itself can be very predictive. And originally that was our intent, to not have to do any feature engineering. But if you added some even like simple features to our model, that could actually enhance performance. We also found a major problem with the home and away field team distinctions. We wanted to have that, but we discovered the model kind of overcompensates and might overpredict a bunch of home team wins. There are a bunch of ways that we could improve model performance, including hyperparameter tuning, experimenting with different features. And as we said before, that wasn't really the intent, but that could actually improve performance, and adapting the model architecture to better match our task. In addition, we can try applying the model to different situations. We can apply it to different areas in the domain of sports, for example, football or baseball, or we could go outside of that completely. And we could do any sort of task that involves edge classification. For example, if you want to predict that there's going to be different types of flight delays, or based on previous performance in school, how is a student going to do in future classes? And finally, we can develop new tasks for the model. Instead of predicting match outcomes, what we can do instead is recommend the best players for a lineup of a team. That's our presentation.
All right, let's give him a hand. Any questions for the team here? Rachel, seeing anything online? All right, thanks so much, gentlemen. Appreciate it. Next up is team Walk Explorer, you're up. And then if you just want to close out that, oh. Give it a second. Is that a good bet?
Share your screen. There's nothing now.
Okay, yeah, so you need to reshare. And then you're unmuted. Good.
Got it.
Cool. Very good.
Hello everyone, this is Team Walk Explorer. I am Siddhi and these are my teammates Ankita and Felix. Firstly, we would like to express our gratitude to our advisor Dr. Wanbe for all the guidance and support. So to begin with, we worked on developing a system that recommends most walkable paths from one location to another based on the walkability scores calculated using OpenAI's CLIP model and K-loopless path algorithm, also known as Yen's algorithm. Today, as our cities grow and change, the quest for sustainable and inclusive urban mobility has become important. Central to this transformation is the concept of walkability. It's not just about creating paths, it's about understanding what makes these paths inviting, safe, and enjoyable for everyone. By utilizing technologies like street view images, multimodal contrastive learning, and distance algorithm, We are not only analyzing the streets, we are interpreting the very essence of what it makes to walk in our cities. Our project is a step towards reimagining urban spaces where technology meets human-centric designs to pave the way for a future where every step counts towards a healthier and more connected world. Urban areas, especially bustling cities like Seattle downtown area, often suffer from inadequate pedestrian infrastructure, making navigation difficult, unsafe, and less enjoyable for residents and visitors. This impacts urban mobility, diminishes the quality of life, and reduces the area's appeal to the tourists. Our project addresses these challenges by developing a path recommendation system, utilizing machine learning models for understanding perceived walkability. We aim to offer users personalized high walkability routes. So our data foundation is built on Seattle downtown street view images and metadata sourced from Google Street View API with over 26,000 images. So this is our system framework. Our system framework is structured in 3 phases. The phase 1 involves collecting street view images from Seattle downtown area and using the CLIP model to calculate the walkability scores. Our original contribution is phase 2 and phase 3. In phase 2, we compute the perceived walkability score for segments from the results of CLIP model. We then employ Yen's algorithm, an extension of Dijkstra's algorithm, to identify the top 3 walkable paths. And in phase 3, it concludes in a user interface that displays these paths on an open street map based on the user inputted origins and destination.
For calculating the walkability score, we have used the CLIP model. Let's get to the background of CLIP model. In CLIP model, we take 2 types of input. One is the text input and the another is the image input. For the text input, we have considered 40 different types of prompts, and the image inputs are the 26,000 street view images we have taken. The prompts further we have classified as the favorable factors and unfavorable factors for the calculation of our walkability score. Now, this study, this is a study performed in the Amsterdam city, and what they have done is they have calculated the walkability score for this area. It's like a heat map they have plotted, and which are the most walkable area. For our solution, what we are doing, we are using this walkability score, and we are trying to provide the user with which is the most walkable path using this reference as a score. In the following study, they have used the CLIP model. In the CLIP model, they are trying to divide how the area is divided into different types of location. For example, if this is a commercial area, is this the residential area? And they have categorized in 5 ways. The prompts which they have used for the CLIP model are specially tailored for this type of land use detection. But for our project, our prompts are tailored just for the walkability index. Now, I would like to with the help of an example, I'd like to show. These are the 2 images. The left image, the walkability score is quite low, and the right image, the walkability score is quite high. The reason this score is less on the left score is because the CLIP model is able to predict that there is a high percentage of graffiti in the wall. As we know that this is not a very good factor when we are considering walking. And as mentioned before, this is considered as unfavorable factor, so the score is quite low. And in the right image, what we have considered, there's green belt because there's a lot of probability. It is evident from the image, and the walkability score is quite high.
Initially, we extract the node and edges geodata frames from the graph of walk network type. To calculate the path with the highest walkability score, we need to compute the weight of each edge in the graph. The image location and their corresponding score are displayed. By averaging the score of all images along an edge, from the list of coordinates in the geometry attribute, we obtain the weight for a particular edge. Given the average score for the edges, we need to invert the scale so that we can use the inbuilt functions to find the path with the highest walkability scores. After modifying the edges geodata frame, we create a new multi-die graph, which is used for the path construction. This is how we constructed the path from a Space Needle to nanoscreen T using the K-loopless path algorithm. On the left, given the multi-digraph we create in the previous step, we computed the first 3 paths with the highest walkability score shown by different colors. On the right, the legend displays the total score for each path and their corresponding top 10 contributing factors as pros and cons. As you may have noticed, the factors along these 3 paths are very similar. This is because each path differs each other by only a few edges.
Now we have performed the different types of experiments using the cliff model and the path algorithm. Now let's head towards the evaluation. This is the evaluation for the cliff model. For this, we have performed a human survey. There are 54 participants and the survey is divided into 2 parts. The part 1, we have provided 2 images to the participants, and then we have asked them, according to them, what is the most walkable path according to the image. And these are the scores which we have received from the cliff model. And this is a result of one of the questions which we had in our survey. It is evident that most of the people thought the second image is more walkable according to their interpretation, and the first image is not that much walkable. And we have received the same result from the cliff model. And for this part, we have got an accuracy of around 65%. And this is the second part of the survey. In this, we have given an image and we have provided the user with 6 prompts. The first 3 prompts are the highest probability which we have received from the cliff model, and the last 3 prompts are with the lowest probabilities. And from the results, it's shown that most of the people thought that most of the results are in the first 3 prompts. And for this part, we have received an accuracy of 85%. Now let's begin with the demo part of our project. So as I mentioned that we are using 40 prompts. These are exactly some of the prompts which I have here. And we have used the prompt, and with the help of this prompt, we are calculating the walkability score. We have further divided it into favorable factors and unfavorable factors. We have used the logic. Now let's try to understand with examples of 2 images. This is image number 1. This is image number 2. Now we'll be redirected to the notebook in which we have calculated. So for this, we have called the cliff model from the hugging faces, and here are the prompts. And then we have given like an index, as I mentioned before, that we have divided into favorable and non-favorable factors. And for that, we have given a direction like 1 is for favorable factors -1. This is a logic for getting the probabilities from the cliff model. These are the 40 different probabilities from the prompt we have received for example number 1 and shown before. And these are the 40 different probabilities we have received for the prompt number 2. So this prompt has got the highest probability, and the 2 other following prompts. And with the help of this and entropy factor, we have got the walkability score here for image number 1. This is image number 2 example. And the highest factor is here. They are public buildings, and it is quite evident from the photo that we are able to see the public buildings. And this is the walkability score which we have received for this image.
Okay, so now let's join Kevin, a recent tech transplant, while he explores Seattle. In the previous slide, we see that he started from Space Needle and make his way to nanoscreen T for lunch. After finishing his matcha latte and a chicken namban, he takes a minute to appreciate the interior design aesthetic of the dining area, and then plots his route back to his new home, which is a 7th and James apartment. Now let's just execute the code from nanoscreen T to the 7th and James apartment. Then we can skip the execution time. Let's look at the paths constructed. The path finding system generates 3 different paths. In descending order, we see that Kevin chooses the highest score route shown here in blue. Note that the second and the third routes are overlapped due to a minimal edge difference. The blue route highlights the maximum amount of open green zone besides the road and the least number of construction on the sidewalk. Now let's go back to the code. This time, after recharging his phone and unpacking a box in Central, he plots another route to Kinokuniya bookstore, hoping to find new stationery and the latest volume of his favorite manga. Then let's execute the code using the origin as the 7th and James apartment and the destination as the Kinokuniya books. So Once the path is generated, again, we see that Kevin chose the blue route again, as it offers more open green zone besides the road versus the red and blue path. Additionally, the red and purple path also show high number of narrow sidewalk. For future work, we aim to incorporate the geospatial data, focusing on street elevation to tailor the path that consider physical effort and individual preferences. Regarding the CLIP model evaluation, additional research is required to develop appropriate quantitative metrics beyond the analysis based on human surveys. To enhance the path construction algorithm, we aim to ensure that the generated path not only meet but also align closely with the predefined user needs and criteria. This approach aims to be comprehensive with the goal to achieve the accuracy and efficiency of the pathfinding system based on the user needs and satisfaction.
The learnings, as I mentioned, that we have used human survey and like for us as humans, we consider different factors when we are trying to walk. So we were trying to use a flip model and try to consider all those factors, like is this path safe? Is it comfortable to go? Are there any good cafes under the factor of attractiveness? And the thing is like a flip model is type of a transformer model, and we have got the score with it, and we have also used like a Yan's algorithm with using the graph theory. So here we are trying to integrate two different types of concept by getting a solution collaboration. Like we would like to thank our professor who has helped us a lot and to have different type of perspective as well as my teamwork. We have worked together and all this project we have decided on our own. And we could like to acknowledge Dr. Khalivi for helping us with our project. Thank you. Any questions you guys have?
All right, any questions for the Walk Explorer team here? Anything online? All right, great job. And last but certainly not least is our sign language to speech team. So let me get set up here.
So good afternoon. Good afternoon, everyone. I am Karthik, and these are my teammates Rakesh and Alfin. Today we are here to present. Today we are here to present our data science capstone project on sign language to speech conversion. So before we begin, we want to thank our advisor Vanbe for supporting us throughout our capstone project. So let's get started. So before getting into the nitty-gritty of our project, let me take a moment to talk to you all about the motivation behind our project. So American Sign Language is used by over 500,000 Americans, but yet there is a significant gap in communication users between the ASL and non-ASL users. And to make matter worse, there are certain societal barriers that widen this gap. So to begin with, there is a lack of awareness about American Sign Language and the sign language in general. So furthermore, there is also limited access to the assistive technologies overall. So, and also at this point of time, the existing sign language, the existing sign language recognition systems offer live translations at either the character level or for a very few or very small subset of specific words. So, we propose a system for real-time sign language to speech conversion at the world level. Firstly, the ASL gestures are captured live and then converted into English language equivalent words. And next, an LLM, specifically we used OpenAI GPT 3.5, is utilized to fill in the missing words based on the context of correctly predicted words. So finally, the converted text is transformed into audio and played back live to the user as the signs are being performed. So furthermore, my teammate Rakesh will talk about the system architecture.
So here we have three phases in our system architecture. Phase one, where we take input as a live video, and then in phase two, we convert it into sign to speech, and in third, we give output. So in the first step, the phase one, we take input as a live video, and then convert it into a specific answer input, which I3D model takes, and then we from the video processing, we send it to MediaPipe, where MediaPipe detects and capture frames for our I3D model. So for then phase two, the batch of frames which are provided by MediaPipe are sent to I3D model, which is our base model, and we train it on our WSL dataset. The I3D model works like into system architecture, where it takes RGB frames and optical flow to understand the motion in the video. Further, the I3D model will convert the signs which are performed into words. So I3D model gives us words with confidence level. So if the confidence of the word is less than 0.5, it will send into the which will predict the word. If the word is like have threshold more than 0.5, it will directly send it to the speech conversion, and also it will send it to LLM, because we need to predict next word, we need to know the previous words. So and then we have GTDS for speech conversion. After the words are predicted, they are sent to the GTDS. The GTDS will convert them into speech and further send it to phase three, which is output. So here we have a basic HTML where you can see camera feed and the output given by the GTDS is in speech. So and also we get output in text. So the content will show the camera feed, the text, and the audio. Furthermore, on the data set, we use a WSL set which have like 2,000 words with 12,000 plus videos at word level sign language detection. So the video have features short video clips of sign language gestures, and those are corresponding to the gloss. Gloss is word which is a sign present. Each video has like 30 frame rates with 5 seconds of duration. And this is how our data set looks like. Further moving to the experimental results, when we trained our model on the data set, so we firstly use like 400 epochs. We can see we got accuracy of 40%. And the graph shows the work fit in the model. So we tried early stocking technique, which gave us the second output, when you can see we ran like 150 epochs and we got model accuracy of 46%. So due to computational resources, we would have like only trained with a few data sets. As this 12,000 video data set took us to like 18 hours to get this results. So we also had different data sets with more videos, but we cannot execute the less computational resources. Furthermore, the demo will be by
Okay. So let's get into the demo. I'll be playing the video and talking with it. I will present the demo of our project. First, I will click on Start Conversion, and then I will perform 4 individual signs. This is the sign for pool. Notice the captions. There is a sign for lava. This is the sign for tank. 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 This is the sign for worry. Worry. What? Say. So this is the current state of the system, and now I'll be presenting the demo of possible future extensions once we have more computational resources and we can increase the accuracy of the model further. Talking about future work direction for our project. Once we have a strong sign gesture prediction model with robust accuracy score, we can generate sentences with the predicted words and feed them into the LLM model. The model will then utilize to form clear and cohesive sentences without any missing words. For the text-to-speech aspect of the project, we could integrate custom voice and accent selection options. It is an example of what that would look like. LLM model with a sentence with a few missing words. Next, I will select an accent, say the Canadian accent. Now, when I hit submit, the LLM will output a clear and concise sentence that resembles our day-to-day conversations. As you can see here, for my input of the sentence, I wore my neatly dashed school today. The LLM gave me an output of I wore my neatly pressed school uniform to school today. Finally, converted audio, the sentence would be read out to me in my selected Canadian accent.
I wore my neatly pressed school uniform to school today.
So moving on to the future work. Beyond the scope of this 10-week endeavor, we hope to extend this project by dedicating our efforts towards these following goals. Firstly, we'd like to perform sentence level sign language prediction. Then we'd like to investigate new video processing techniques that will help us improve the accuracy of the core model. And for number 3, we are planning to work on API development so that our pro models can be integrated with third-party video conferencing softwares like Zoom and Teams. And for our project learnings, while we have certainly learned a lot of things and made some mistakes and learned from them, there are 3 things that stand out. Firstly, we have gained practical experience in applying the data science methodology to solve real-world problems. And secondly, we learned about techniques to handle video data for machine learning models that are geared towards user-centric applications. And lastly, we learned the importance of integrating different areas of AI and ML for achieving contextually relevant and apt solutions for the data science problems that we have at hand. And
Finally, we'd like to thank our professor and the project center team for helping us here today. And we are really glad with what we have performed, and we hope you liked our presentation today.
All right, questions for our final presentation today?
I have one ambiguity about what you did was converting the gesture into one word.
Yeah.
ChatGPT, if there are missing words in one sentence, it matters. I wasn't sure what is the role of ChatGPT there. Yeah, so the threshold of the confidence is like less than 0.5. We send it to the LLM. But it's more than 0.5, we use about it. So you're saving whatever the we using those words. We using word buffer to save the words. Thank you.
Anything else? All right, thanks so much, Tim. We appreciate it. Well, and that concludes NSCS project. Address, it's mhamilton3@seattleU.edu. You probably received several emails from me. So just shoot me a note if you'd like a copy of this presentation. But overall, thanks to everybody for coming out and supporting the effort today. And special thanks to Dr. Wanbei for partnering with the project.
Many thanks. Thanks, guys. Good job. Good job.